And it's good experience.
All right, tell you what. Thank you. Guys, what I want to do is cover two things, and then I'll take your questions. And I need a homework problems. The first is that moving average filter. I want to finish this and make sure it's done right. This is useful. Now, hear me now. A lot of times in the real world, you're going to get data that's noisy, very noisy. The first thing you can do, without getting into the high-level filtering like Kalman filtering, the basic things, and Excel, things like that can do this for you very quickly. This is called the moving average filter. What it does is take values, maybe 3 or 4 values, the present value and the 3 past values, adds them up and divides by the number. It gets an average. What it does is get rid of the high-frequency jitter and noise. It's often associated with these things. So, in general, if you have a filter, say it's Y of n, it's going to be a simple filter. It's just going to take 1 over a certain number of samples. And it's going to add the samples. It'll take x of n plus x of n minus 1 plus x of n minus 2 plus dot, 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 plus x of, and then it'll be n here minus really quantity n minus 1. The reason it's n minus 1 is we already started here. That's the first one. So there are n samples. Do you follow me? I didn't write that in terms of the sum. I just expressed the whole thing so you see it. You follow me on this, everybody? I could write it in terms of the sum, but then I get 2 sums that get a little annoying. You'll see why in a second. Now, if you just look at that, that's a moving average filter for any number of terms. I have n terms that I'm adding up. And this is really useful for stock market analysis and just about any type of data where you get a lot of jitter. They call it jitter. And you want to get rid of it. You want to take a look at the low frequency. Now remember, this is in the discrete time domain. So if we take the z transform of this, what you end up getting is y of z here. And by the way, we're assuming no initial conditions. You can't ever have one of these things working for you and assume you have to start it at 0 with initial conditions. That is something that's going on, and it's assumed all the initial values, you might say, the response from the initial values is gone. It's died out. So now we take a look at this. This is y of z is equal to 1 over n. And now I have x of z, right? Now just follow me on this. That's just x of z, right? The next one is going to be z to the minus 1 times x of z, correct? Mm-hmm. This one will be x, or it'll be z to the minus 2 times x of z, and so forth all the way over here till I have z to the minus n minus 1 times x of z. Follow me? So I factor the x of z out of all of them, and I get this. 1 plus z to the minus 1 plus z to the minus 2 plus dot, 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 plus z to the minus n minus 1. You all follow me on that? Here I'm just doing the z transform of the initial summation that's added to the average. Does that make sense? Mm-hmm. Everybody see that? Now I take a look at this, and I can say that I can express this y of z over x of z here as the transfer function h of z, and I can say that's equal to 1 over n, and now I have the summation here, right, of the quantity z to the minus 1, quantity 2, and you can call it n power, from n equals 0 to n minus 1. Just notice what I've done there is now define that series that I had discretely shown in terms of the summation sign. You all see this? Make sure you convince yourself that what I've done there is just a shorthand way of looking at it. Now, this is the characteristic sum that I showed you some time ago. You don't need to write this down, but I'm going to put it up here for your benefit. Do you remember if I told you if you had a summation where n equals 0 to some quantity n minus 1, I'll do n minus 1, of any a to the n, that was equal to a to the 0 minus a to the, and then it would be this plus 1, or just n, over 1 minus a. You all remember that, class? Now, as a variance on this, I have Q1 to Q2 sometimes, right? And this would be Q1, and this would be Q2 plus 1. But in general, I mean, this is an application for what I want. You agree with me? So here, the A that's associated with this sum is z to the minus 1. Do you all agree with me there? So I can say that this is going to be equal to simply 1 over n times, and then it's going to be z to the minus 1, really to the 0 power, minus z to the minus 1 to the n minus 1, or n power, pardon me, just n, over 1 minus z to the minus 1. Please note, the reason I wrote it like that is because I want to make sure you see every single step in this one. Now, do you all agree? Because there'll be times when we're going to have to actually determine what the Z-transform is of a certain type of filter. This one's a straightforward, it's a moving average filter. It's averaging values. You could say at a point, at a value n, it's taking the 3 or 4 or 5 or 6 previous values and adding them all up, and then dividing by the number of values. That's what this is. So it's averaging, but it's moving. It's not starting at 0, it's moving. Follow me? Now when you look at this right here, what is z to the minus 1 to the 0? 1. Just 1. And this is really just z to the minus n. All right. Y'all give me that?
Yes.
How many think they know where I'm going with this? I bet you some of you do. You're sort of suspicious. It's looking too close to something I did earlier. You're right. So this is 1 over n, and I'm going to do this first with z. So I'm going to go ahead and say I multiply. What I can say is if I take this, and I can factor out on top a z to the minus n over 2. And on the bottom, I can factor out a z to the minus 1/2. And then I'm left with z to the n over 2 minus z to the minus n over 2 over z to the 1/2 minus z to the minus 1/2. Please just notice I've taken this and I've factored out a z to the minus n over 2 on top and a z to the minus 1/2 on the bottom. Some of you by this time know exactly what I'm going to do. Now I'm going to, because I want to take a look at the frequency response to this, right? And I know that z in general is equal to some rho times e to the j omega. That's what the z operator entails. But now we let the rho be 1. So for this operation here, we let z, because I really want the frequency domain analysis, z go to just e to the j omega. Now when it does that, this becomes 1 over n times the quantity e to the minus j n omega over 2 over e to the minus j omega over 2. And then here it becomes e to the j n omega over, omega over 2 minus e to the minus j n omega over 2 over e to the j omega over 2 minus e to the minus j omega over 2. I'm putting down everything here. You agree with me? I'm letting z be equal to e to the j omega, right? That means rho is 1 in this case. Well, the reason I did that, now this is the dTFT. This literally is something where the omega is the frequency. It is, frankly, in the frequency domain from minus pi to pi. When we look at this, what am I going to do with this right here? How many know? I know you guys know it. It's a sine, isn't it? E to the j theta minus e to the minus j theta is what? 2j sine of theta, right? Theta in this case is n psi over 2, correct? Same down here, the 2j's cancel. So now I have this thing equal to 1 over n times, and these are phase terms, e to the minus j n psi over 2 over e to the minus j psi over 2. You don't worry about the phase terms on this one. Then it's going to be simply sine of n psi over 2 over the sine of psi over 2. And that, put down, I should break it to the next line, call it h of omega. Now that is the actual frequency domain response of the filter, of the digital filter. Please take a careful look at that. Just notice this part right here, the sine of n psi over 2 over sine of psi over 2. All right? Now I'm going to come back here and do this. I want this part of the board now. Now when you look at this, the next step is I want to take a look at the magnitude of h of omega. When I'm talking about the magnitude of that, I don't care about this term. These are phase terms. That's all they are, aren't they, class? We want the magnitude. The magnitude of this is 1 over n times the magnitude of the sine of n psi over, n omega over 2 divided by the sine of omega over 2, magnitude. Now, I want to tell you one thing. If you're looking at the magnitude of this, at omega equals 0 is what we want to do. First, what I really want to do is plot this, and I want to show you this. I want to plot the magnitude of that filter response right here versus omega. I want to go ideally from minus pi, because that's the entire range of where the DTFT is of interest to us. It repeats itself up and down the axis, but this is the range that's of interest. Now when you look at this, when omega is 0, what's the problem? What's the sine of 0? It's 0, so I got sine of 0 over sine 0 or 0 over 0. Have to use L'Hopital's rule to define what it is, so I take derivative of the top, right? I'm going to pull out the what? N, capital N over 2. Derivative of the bottom is just 1/2, right? And then I get a cosine, it's a minus. I'm going to get the cosine in that business. But when you look at that, evaluate it at omega equals 0, then I got n over 2 divided by 1/2, or n. So that value at 0 is n, but it's divided by n, so its actual value is 1. This is important. Now, the next thing you got to know is the sine of x, or x small. The sine of x is approximately x in radians. Most of you know this. And what do they mean by x small? Usually you're talking about something where you've got pi over, let's see, pi is 180 degrees, so you want to, so it's really about pi over 20. Somewhere in that range would be very small. Nevertheless, if n's a large number, then you can take a look at this. This looks like sine of n psi over 2, about over omega over 2. Follow me on this? This doesn't change very much. This changes a whole lot, the top one, because it's sine of n. The factor of n causes it to oscillate very quickly as for small variations in omega. But the real thing you consider is the first 0, where that function is 0. And the first 0, where it comes down to here, we've done this one other time, would be when n psi over 2 is 0. Isn't sine, think about sine. Sine of 0 is 0, right? Sine of pi over 2 is 1, and then sine of pi is 0, isn't it, class? So what you do is set this argument, it's in radians, equal to pi. So you say n times omega over 2 is pi, or you get 2 pi over n is really the omega, the first 0 that goes here. That's the first 0 there, and minus that would go there. Follow me? Now the second 0, if you cared to find it, would be where n psi over 2 is 2 pi, right? Or it would be 2 pi over n, would be here. And they would be periodic, all these zeros, up and down. And what you do is get this. And it looks very much like a sinc function, where it's asymptotically decreasing out to pi. But the real thing is between here and here, you've got very strong filtering. It's rapidly decreasing, right? Now, listen to me. If you think about a signals and using this type of filter, what it's really doing is rapidly attenuating all the high frequency variations. We can get a very rapid attenuation if we want, but this is a way of getting a fairly high level of attenuation, rapid attenuation, by summing the terms and then dividing by the number, summing backwards, moving average. And that really is called a moving average filter, and how it would affect data. It would have really, this would be the filter effect on whatever x of z, and then take z and turn it into e to the j omega would be. Now, it's really useful in stock market data and things like this. I want to make sure I expose you to that. That's the first type of basic filter. I use this stuff. It works great when you have noisy data. You can just, there's no hard and fast ways I do this. Normally in Excel you can do this real easy too, by the way. Has anybody used one of these in Excel? No, Excel is really easy to work with. You can do it on MATLAB too, but you can just say how many terms in your moving average, and you can and you can start taking a look at another term. All of a sudden, real noisy data. And I'll just tell you what I've seen over and over again. I might see this kind of data. Now I'm talking about this is for discrete time, right? You got all sorts of jumps. Now I start summing them. And after I sum, say, 10 terms, all of a sudden I see this. And then I can see what looks like a sinusoidal or a periodic signal coming out of there. With me? And then I can go ahead and home in on that periodic signal by more exact filtering methods. But that's real useful when a lot of times you don't know what you're looking at. And I do electromagnetic compatibility and electromagnetic interference and electronic warfare and all this other stuff that all boils down to one thing. What signal is really harassing you, or what signals are out there? So what you do is in the spectral domain, you take a look at all this stuff, and it's sample. And there's so much of it, you don't know. Frankly, most of the time you don't know what really is out there by taking just a look at the spectrum. It's too noisy. So you start applying filtering methods. And the first filtering, the easiest one to do, is just a moving average filter. It can usually tell you where the really strong signals are, and you'll get them. After that, you can start, there's more on filter coming, but I'm just trying to tell you how useful something as simple as this is on data analysis. If you ever play with the stock market, make sure you know about moving average filters and weighted moving average filters. They are a godsend. The next filter I'm just going to talk about briefly is an extension of this, and this is called a weighted moving average filter. And the reason for this, it gives you a more exact, see how you have these things right here? Now you can get a more exact taper, and you can get just about any taper you want with a moving average filter. I'm just going to show you what it is. These are useful though. I'm bringing this up because I know it's useful to know this and apply it to data. I remember working with Dr. Riggs on some stuff with mine detection. And instead of going through some elaborate DSP toolbox stuff, we just started with a simple moving average filter, and bingo, it showed what was going on very quickly. It was amazing how fast it identified what the real problem was. So, and that was about 5 years ago. So the next type is called a weighted moving average filter. This is a weighted moving average filter. And as you might guess, you're going to have a certain number of samples. I'm saying there's n samples. But now, what I'm going to do is say the samples closest to the value of n will have the strongest effect. So I'm going to weight them the strongest. So what I'll do is say I have x of n here times a to the 0 plus a to the 1 times x of n minus 1 plus a squared times x of n minus 2 plus dot 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 plus a, and then it would be to the n minus 1 times x of small n minus quantity n minus 1. Now you can see here the value of a is critical. If a is greater than 1, I'm weighing the values furthest away the most. If a is less than 1, I'm weighing the values closest to n, x of n the most, right? And typically for this one, magnitude of a is less than 1. Typically, this is a common filter, by the way. It's very commonly done. Y'all see what I'm really up to here? This is a weight, I'm weighting each value. And it doesn't have to be this form. You know, I've got a here, where a is some value, some constant. It can be much more complex than this, but it's easiest. This is the easiest one to see. And by the way, whenever you're doing something like this, always start as simple as possible when you do filtering. Don't ever, you know, come out and, you know, I've read about a Kalman filter being so powerful, I'll apply that. You usually, when you get these sophisticated filtering schemes, you also build in unforeseen problems, lots of problems you don't know about. So the simpler the better. That's the general rule of thumb whenever you're doing filtering. Start simple and look for what you're after. I mean, look for trends. Now on this one, now you take the Z transform of everything, right? Correct, class? And if you want to do this, what happens, if you just take a look at this, I can say that I have y of z here is equal to 1 over n, and then it's going to be times what? I can take x of z out of all of there, I think, right? Now I have this sum of a to the 0, well, I'll write it down. I'm going to have a to the 0 times 1 plus a to the 1 z to the minus 1 plus a squared z to the minus 2 plus dot 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 plus a to the n minus 1 times z to the minus quantity n minus 1. And I only have this. Y'all follow me what I've done here? I've taken the z transform, so this x minus 1 brings out a z to the minus 1, x minus 2, z to the minus 2. Follow me on this one, guys? But I left the sum here because that really, these coefficients, right, aren't changing with small n, right? They're just being added, they're summed. Correct, class? Now look here, what happens? How can I rewrite this? Well, can't I rewrite this as simply y of z over x of z is equal to 1 over n, and then I can take the sum here, right, and I can take a over z, right, to the n, where n goes from 0 to n minus 1. Please just take a look at that. That's supposed to be a z, a over z. Do y'all see that? Make sure you're convinced that that's what it is. Looks almost identical to the previous one, except for instead of z being summed, what do I have? A over z, correct, class? So I erased that little guy over there, but now I know that this sum here becomes what? That becomes 1 over n, right? And now I'm going to have quantity, I'm going to put them up here, it's going to be this to the 0 or 1 minus this, a over z here, to the n over 1 minus, and then it's going to be a over z. All right, do y'all agree with that? I'm using that definition of what the sum goes to, right? Y'all remember that, class? You can put it up if you want to, but that's what it's going to go to. Now, when you look at this one, right here, how about if I make it a little bigger? I'll put, this is 1 over n here. And then what I can do is I can have 1 minus, and this would be Are you with me? Now, here's the deal with this one. You can do this a couple different ways, but when I look at that, I can say, I mean, even this one, I can factor, because when I've got there, what I have right here, when I have A over Z, I'm gonna let Z become equal to E to the J omega. That means I have E to the E to the minus J omega here, don't I? Are you with me here, class? Isn't that right? Now, if I take a look at that, it depends how far I want to go with this. I can take this, probably at that point, just making that transition for whatever A is. I can put this in here, and I could put Z equal to E to the J omega into these two things. And, you know, because you've got computers right here, the easiest thing in the world probably is just taking the magnitude of this and plotting it. All right, I can fuss with this thing, I can get a weight on a sine wave out here, but if you just plot this thing, and I might put this up for a homework for another extra credit, and mess with it, what you can do is then tailor that filtering profile, the way you want to get it. Now, you can take a look down here. Here's where it gets interesting. Look down here, when Z is approaching 0, you can see that if A is 1, we get a singularity right here, right? And that's with the sine business. When you turn it into a sine, you get that stuff. But this is another thing, I probably should have you do a homework with this as a type of filtering so you'll see it for yourself. But it's a powerful way of really filtering data. Now, when I think Dr. Hung will talk about John Hung in his class on controls, but for sure Dr. Reeves in his digital signals class and his really digital image processing and digital signal processing classes, you'll get a lot of this, and it's very, very valuable. I want to just expose you to it, all right? Now I'm going to do something else next. That's a weighted moving average filter. Next thing, I want to do, really just talk about this, it's a simple problem, so I want to do one of these things before I take the questions. When we have H of Z here, this is part of the homework I gave you. I want to run through this one, and I want to discuss all aspects of it before I continue. I'll get to the rest of the questions, but let me just do this one. There's going to be Z minus 1, Z minus 6, this is the first one I think, over Z minus 2, pardon me? Z minus 3, I think it's the first one.
Yeah.
We're going to actually take a look at this in the complex plane and talk about it. First thing you look at is the zeros. What makes this thing go to 0? Well, obviously if this term is 0, H of Z is 0. Or if this term is 0, H of Z is 0, assuming all other terms don't have a singularity, or have a 0, I should say. So we know that these are called the zeros. And the zeros right here are simply at 1 and 6. ZB equal to 1 and 6. I think everybody can see that. The poles are the value of Z that makes it go to infinity. Makes it looks like it's just sticking straight up into infinity. So the poles are at 2 and 3, right? Now, anytime a pole is at 1 or greater than 1 on a system, when you're doing a Z transform, it means the system is inherently unstable. Only for a very small class inputs will you get a stable output. But systems like that are valuable when you're dealing with, when you want a huge amount of change happening to a system with very little input. And I gave you an example, and I don't have time to go through the real reason behind this, but I think I mentioned X-29 submarine fighter before, didn't I? Mm-hmm. All right, that flies unstable. It means, simply put, if the electronic controls, for whatever reason, are disengaged, then it spins in a way that's destructive. It's just going to tumble and blow apart. It's unstable. But the advantage is, with a very small amount, you might say input, it can do incredible turns and things like this. It can outmaneuver anything. But it's a deadly thing, because if you get a failure, the guy's dead. So it doesn't work well with real pilots. Now, on this one, the way you figure out stability, and the way they always do this, you plot this in the z-plane, and it's just like the s-plane. You're going to have real values here, and you're going to have imaginary values here. And when you look at, for instance, the poles, you notice you got a pole at 2, which means you take a radial distance of 2, and then you say e to the j omega, where omega can go from 0 all the way to 2 pi, like that. And it says, because of that pole, it says that the value of z has to be greater than 2 for this thing to be stable. Not only that, you also have a pole at 3, e to the j omega. This is defined in your book a lot better. And you'll see a circle like this. And whenever you have 2 poles, the outermost pole is the one you worry about. So the region of convergence, this will mean a lot more later. The region of convergence for this particular function, called ROC, is really for magnitude of z greater than 3. Understand? It would be stable if z, if the pole was at z less than 1. But since it's greater than 1, it's unstable. All right? And in the book, we went through some of this with you, all right? Do you remember doing some of these things where we actually got the h of n and we saw it like you got 2 to the n. It's growing exponentially, right? 2 to the n u. So this thing is inherently unstable, but we've got 2 poles here. And we've got zeros at 1 and 6. You don't even really worry about the zeros. For zeros at z 1 and 6, usually what they just do on the real axis, they'll go at 1 here, I'm sorry, 1 and then 6 here, and you'll just have this. You'll just see a 0 there, and that's it. Now the next thing, oh yeah, we're going to talk about the differential equation that this came from, or the difference equation. The way you get this is, I'll say it over here, h of z. Most of you know this, but I'm doing it, so I'm going to hopefully get any questions right here, and I can answer sequentially. I multiply through here, I have z squared, right? And then I have minus 7z on top. And then I have plus 6. Then I have z squared, what is it, minus 5z, right?
Yes, sir.
5z, and then I have plus 6. So I have that. Now I go ahead and divide top and bottom by z squared, and I get 1 minus 7z to the minus 1 plus 6z to the minus 2 over 1 minus 5z to the minus 1 plus 6z to the minus 2. And that's equal to y of z over x of z. Which means I have y of z. Please, if you didn't do the homework, watch this carefully. And then I have 1 minus 7z to the minus 1 plus 6z to the minus 2 here equal to x of z I'm sorry, this should be x of z right here. My bad. This is x of z here, and this is going to be y of z.
So you said you divided everything by z?
Z squared here.
Okay.
So you got 1 minus 7z to the minus 1 plus 6z to the minus 2. 1 top and bottom by z.
Yes.
It's
Okay.
5z to the minus 1 plus 6z to the minus 2. And this is going to be y of z on this side. And then it's 1 minus 5z to the minus 1 plus 6z to the minus 2. I'm doing this whole thing one time. I know it's, if you look through it, it's pretty obvious, but just bear with me. Now I want the differential equation it comes from. Again, whenever you're getting a problem like this, unless somewhere it's explicitly stated there are initial conditions that are not equal to 0. In other words, either an x or a y of minus 1, it's stated explicitly. You have to assume that, all right? Because this is considered, once you're in that form right there, you don't know where it came from, but you usually assume there were no initial conditions that brought that about, unless there's some reason to believe otherwise. Now I come down here, and I know that every time I get an x to n minus 1, when I take the transform, I get a z to the minus 1. Whenever I get an x of n minus 2, right, I get a z to the minus 2 in front of it when I take a transform. So therefore, the difference equation to this would be x of n, right here, minus 7 times x of n minus 1, that's because it's z to the minus 1, plus 6 times x of n minus 2 equal to y of n, that's the first one going to the other, minus 5 times y of n minus 1 plus 6 times y of n minus 2. And that's the difference equation that would give you, render that h of z. Now, listen to me about this one. With this equation alone, I can set everything y of n equal to all this stuff. If I took this and this to the other side, I'm about to do that. So I can take 5y of n minus 1 on that side, and then minus 6y of n minus 2 here. And now I have y of n on this side. Typically, you put y of n on the left than what it's equal to on the right, but this is backwards. You agree with me? Now, you can do this in MATLAB very easy. You'll see, if you did something, you made a chart, you could have n here, then x of n, and then y of n. All right? Here. Now, or, yeah, like for that. When n is 0, you have x of 0, y of 0. 1, x of 1, y of 1. Follow me on this one? So if you start at n equals 0, no initial conditions. I look here, that's not there, that's not there, right? That's not there, that's not there. The only thing that matters is x of n. Follow me? Whatever the value of x of n is, it translates to y of n. Follow me? Then you would put that in there for y of 0 and x of 0, because I'm saying n is 0. Now the next one here, y of 1, now n minus 2 I don't care about, but x of n minus 1 I care about. Follow me? And you go ahead and you can assemble this thing sequentially that way. It's a recursive relationship that you can do. I don't really want to get into it right now, but you all understand how that's possible. Right? Now, on this problem, I think, was there another part to that they asked in the first problem or not?
Yeah, there is four.
What did they ask? Finally? Say again?
They asked for like responses to inputs.
All right, so what input?
X of n is equal to bracket 2.
Oh, okay, hang on for 1 second. This is y of n minus 1. X of n equal bracket
2, negative 6, 4. And that's it.
All right, so I'm assuming this is n equals 0.
Yes.
Here, you can do it either way, but this is so simple, just looking at this thing, what I've done here. All right? I'm going to go ahead and say y of 0, all right, would be associated with this value from n. Is it 2 in the beginning?
Yeah, 2.
All right, so I come over here and I just say y of n. There ain't no n minus 2, there ain't no n minus 1 to worry about. It's just going to be equal to x of n or 2.
That's not, those are the wrong numbers
Oh, it is?
for that problem.
I was on the bottom one.
All right, what are the right numbers?
1, negative 5,
1,
6. Negative 5, 6.
are those the right numbers? Well, do it with me. Come over here. I take a look at this. N equals 0. X of 0 is 1. So 1, 1. All these other things are 0. So it's y of 0 is 1. Agreed? Now, y of 1, this is when n equals 1. N minus 1 is equal to 0, correct? Make sure you follow me on this one. Just look at this, and we'll go through it. Do we need to worry about that term, class? No, that's n minus 2, right? We don't need to worry about that term either, right? But we need to worry about everything else. So with n minus 1 in this case is 0, which would be 1, right? Y of n minus 1 is y of 0 is 1. I don't have to worry about the next one, plus x of, now this is going to be, n is 1 is minus 5, isn't it? You follow me on that? Right, take a look, the second, right, we're on the second number, right? N is 1, the second number there is minus 5. Then I have minus 7, right? Times x of 1 minus 1 is x of 0. X of 0 is 1, right? So it's 7 times 1 is just 7, right? Then it's equals, there is no x minus 2 to worry about, so that's y of 1 here. And you can see that's what? That's going to be minus 12 plus 1 is going to be minus 11. Correct, class?
I think that's supposed to be a 5 instead of a 1 right there, because it's 5y and minus 1. You just erased it.
Here, we'll do it, why don't I do it right here? Follow me on this. Y of n minus 1 is y of 0, right?
It's supposed to be 5y and minus 1.
Oh,
Yeah.
sorry. My bad. So that's 5, I'm sorry, then 5,
Yes.
right? Then it's going to be minus 6 times, not minus 6, plus x of minus 5, right?
Yes.
So it's minus 5, and then it's going to be minus 7 times 1, right? X of n minus 1 is going to be 7 times 1 right here, right? So minus, and then that should be it, which is really going to be just minus 7, correct? I'm doing it this way, there's another way to do it. I don't know if they did it the other way or not, but. Next one, y of 2, do it here with me. You can see what I'm going to do. When n equal 2, n minus 1 is 1, n minus 2 is 0, no? Correct, class? It's just plug and chug here. If you want to do it recursive. How far out did they take this, by the way? For the answers. How many values of y? Just 3?
Yeah.
All right, well, 3 values it is. So finally, if for y here of 2, that's equal to 5 times y of 1, which is going to be minus 7, minus 6 times y of 0, which is 1, plus 6, that's x of n, minus 7 times x of 7 times minus 5, right guys? X of n minus 1 is 1, and x of 1 is minus 5. Right here, it should be a minus 5. If I want to do it this way. And then plus 6 times 1. And what do you get for that? I see I got minus 6 plus 6 cancels. Then I got 5 times minus 7 and minus 7 times minus. That cancels, so it looks like I get 6 for this one.
How did you get 6 times 1 at the end? For the x of n minus 2?
Well, but when I look at this, this is for n equal 2. So 2 minus 2 is x of 0 here. X of 0 is the first entry, 1. So it's going to be 1 times 6.
Okay.
How many see this right here? It's recursive. You don't have to do it this way, but it's easier, in my opinion. Did they do it this way in the book or not? What did they do?
They had h of z and they took x of z multiplied.
All right, you can do that too, but honestly, the recursive way is easy too, I think, because it's obvious too. I mean, you can do it either way, but doing it recursively for a problem like this is pretty trivial. You should be exposed to that too, because by the way, in real time, when you do this kind of stuff, you're basically doing that in real time. You can't take a Z transform of all the data, you don't have it. You know, in real time, the only thing you can do is implement a recursive relationship like that. Now, questions about any of the,
It had one.
huh?
It had a.
What else?
The impulse response, H
All right. Well, we can do that fairly quick, but we can get h of n. So the original function was what? H of z was equal to
Z minus 1 times z minus 6.
6 over,
Z minus 2 times z minus 3.
now, since the power of the denominator is same as the power of the numerator, got to divide by z, right? Here. And if I divide by z, I can do it as simply as this. You with me on this, guys? I can just put a 1 over z in front of it. Now, I know, looking at this, I've got what? Now I've got 3 poles. I have some C1 over Z, or C0 over Z, plus C1 over Z minus 2, plus C2 over Z minus 3. Do y'all agree with me there? Are you with me? Everybody? All right, now take a look at that. What is C0? Pole is at Z equal
0.
at 0, right? So how do I do it? Cover this up, right? And let everything, let Z be 0, so I have -1 minus 6 is 6 up top,
6 over 6 or 1.
or 1. So C0 is 1. How do you get C1? Anyone?
Z equals 2.
So cover up Z minus 2, right? And then let Z equal 2, what do I get? 2 minus 1 is 1, right? 2 minus 6 is minus 4. So I have minus 4 on top, right? And then I have 2 minus 3 is minus 1, so minus 1 into minus 4 is going to be
4.
simply 4. And then I have 2, so it's going to be 2, right? What's C2, anyone? Who can do it? I'm going to cover that up, right? I'm going to let Z equal 3, correct, class? 3 minus 1 is 2. 3 minus 6 is minus 3, right? So I'm going to have 2,
Should be just -2.
2 minus 3, correct? It's going to be minus 6, and then what do I get on the bottom? I get 1, and I get 3, so is that minus 3, class? Is that what you get?
Minus 2.
Minus 2? Is that minus 2?
Yeah.
I'll trust you on that one. I'm trying to get this done. Now let's take it back. What do? We have to multiply by Z, don't we? We divided by, now we multiply by Z. Correct, class? Multiply by Z. That's 1. That's Z. That's Z. Help me out. What does 1 go to?
Delta.
Plus this one, 2 times class to the n u of n. You agree with that? Minus 2 times 3 to the n u of n. Is that what he has? He doesn't? Josh, does he have that? What did he do? Just give me a second, let's figure this out. What does he have? Tell you what, do this with me. You look at what he has and do this. When n is equal to 0, what do we get? N equals 0, we get what? 1, right? What is 2 to the 0?
1.
So it's 2 plus 2, right? Plus or minus 2, right? Or we get 1. Take a look at n equals 0 in his answer. Does he have 1? Is the value of that 1, Josh, or not? For however kind of crazy answer he has. He might have an a minus 1 in there or something.
Okay. He's got h of n equal to delta of n plus 4 times 2 to the n minus 1
Oh, he's
u of
doing
n minus 1.
Just put n, or let n equal 0. Tell me what you get for that. Delta n is 1, right? All the other terms better be 0 in his.
Yeah.
Are they? 5, I'll bet you $5 this answer is the same as his answer, just in a slightly different form. You got it? It's easier to do this way, in my opinion. Okay? All right, was there another question for you? I wanted to do this moving average filter show with you today. Did you have a question? Did you have another question? All right, and now all the rest follow the same trend, don't they? If you look at all of them, they're a little more complicated. The one thing I didn't have a chance to get at is the frequency response. I'm going to do this on Friday. I'll get bombarded by questions about the quiz. The quiz is going to be on the Z-transform stuff from this homework and the prior one. Right? So you basically know how to take a Z-transform to a difference equation, be able to find the poles, the zeros, find out if it's stable or unstable, which is pretty easy, and also evaluate output for a given input. All right, now I'm not going to give you anything more. stuff that's simple and straight. If you look at any of the quizzes I give you, pretty much they follow the trends in the previous 3 homeworks with not much variation. Just remember that, but you can have to do the homework. I just want all of them.